Welcome back to the Rock the JVM channel, folks. I'm Daniel, and in this video I'm going to continue where we left off with FS2 in Scala. So this will assume that obviously you're comfortable writing Scala and some basic FS2 concepts such as creation and transformation of essential streams. I have a video here on the Rock the JVM channel where I describe exactly that, so go ahead and watch that if you haven't done so already. As a bonus, this video will be much more comprehensible for you if you also have some basic concepts about Katz effect, which I describe also here on the Rock the JVM channel and in great detail on the course at the Rock the JVM website. Of course, I recommend that you code with me in this video, and whenever you need to refresh your memory about FS2, just refer back to this video or to the written form at the blog with the link in the description. So without further ado, I'm back in my IntelliJ project, and I'm going to continue the code that I wrote in the last video. So I'm going to continue the use case with the fictitious IMDb-like application or scenario where we store actors and movies into an imaginary IMDb kind of application. And in this data object, I have a bunch of actors in all the superhero movies in both the DC comics and the Marvel comics. Now, the build.sbt file just contains a single dependency, co-fs2 fs2-core. At the moment of this recording, it's 324. And it's available for both Scala 2 and Scala 3. So this code that I'm going to write in this video, as well as the code in the previous video, is 100% compatible with both Scala 2 and Scala 3 at the time of recording. So in the previous video, we described how streams are created and transformed with a variety of APIs that FS2 allows. Now, in this video, I'm going to start exploring some more advanced concepts, including resource, pipe, and concurrency with streams. And I'm going to start with a pipe. So a pipe is pretty much a function from a stream with an effect type F and some type I to a stream with the same effect type and some other value type O. So a pipe is pretty much a function from a stream to another stream. This is the definition of a stream transformation. And I'm going to demonstrate a simple transformation from an actor stream. And if you remember from the previous video, an actor is simply a data structure with an ID, a first name, and a last name. And I'm going to transform a stream of actors into a stream of strings, for instance. So let's call this actor to string pipe. And the type definition for pipe is pipe, that I'm going to import from FS2. Pipe takes the effect type. In this case, I'm going to use IO. The input type, I'm going to use actor, and the output type is a string. And pipe is literally a type alias from a stream of a particular type to a stream of some other type. So pipe FIO is a stream FI to stream FO. This is literally what a pipe is. It's a function. So considering an input stream, I'm going to say, for instance, inStream.map, and considering an actor, I'm going to return, let's say, actor first name, and then the actor last name. Right, so this is a function from actors to strings. Obviously, you can define some very generic pipes. I'm going to demonstrate a toConsole that takes a type argument A, and this returns a pipe where the effect type is IO, the original value type is A, because I've denoted as such, and the output type is unit because I want to print every single value to the console. So I can say inStream arrow inStream dot eval map, and this is a transformation that we explored in the previous video. Eval map is a flat map where the lambda takes a value and it returns another stream where the value inside of that particular stream is an effect. So I'm going to use eval map with io.println. Now, the way that we can use these pipes is to transform these actors through transformation functions described by pipes. So I can say, let's call this string names printed as the jail actors, and the jail actors from the previous video is a simple stream that contains some values. So you can use the apply method of stream to pass some actual values, and you can find these values on the blog post. You don't have to type them yourself. And considering my Justice League actors, as I've described earlier, I'm going to use the through method that takes a pipe, and I'm going to use actor to string pipe, and then another through, and then I can say to console. So in essence, what I'm saying is that for every actor, I'm going to turn them into a string, and then I'm going to print them to a console as an IO effect. And of course, I can say string names printed, then I'm going to say compile, and then drain to return an IO unit, and I can run this application and see what we get. My compiler is code. All right, so we have all the actors being printed one by one on every line, and the end of this stream is going to be, or rather the type is going to be a stream where the effect type is IO and unit. So you can connect streams together with pipes and the through method. Now, of course, the through method is sufficiently descriptive, but I have a mini problem with it because for non-native English speakers like myself, typing through is a little bit of a burden. Now, not that big, but you could pick the via name, man. So you could say via from Akka streams, and it's super easy to write. All right, anyway. Cool, let's move on to error handling. So let me go ahead and define a simple method. Let's call this save to database. And I'm going to pass an actor as an actor, and I'm going to return an IO int, which is the actor's ID in the database. And I'm going to have IO, and I'm going to say print line, saving, actually gonna start a small string, saving, and I'm going to use the actor's first name. So actor.first name, and let's also inject actor's last name. So actor last name. And let's say that with a random probability, like 50%, this database thing might fail. So if I say random, and I'm going to import random from Scala util, random.nextInt, or next boolean, so next boolean, then I'm going to throw new runtime exception, let's say persistence layer failed, or something like that. And otherwise, I'm going to say print line saved, and then I'm going to return actor.id as the value contained in this effect. Cool. Now, let's try to push all of our actors to this fictitious database. So I'm going to have, let's call this saved jail for Justice League actors as a stream where the effect type is IO and the value type is int, and I'm going to use jail actors dot eval map as we did before, and I'm going to have this save to database method as the argument. Now let me run this stream in my console. So instead of string names printed, I'm going to use this save jail actors, and we're going to see that this effect with pretty high probability fails at least at some point. So saving the first actor saved, and sadly at Gal Gadot we have a failure. Now, how do we recover from failures? We can say handle error with. So I'm going to use, let's say, error handled actors as a stream of IO, and I'm going to place a placeholder here at the moment, and I'm going to use saved jail actors, and I'm going to have handle error with. Handle error with takes a function from a throwable to some other stream. So I'm going to have my error, and I'm going to have stream dot, let's say, I'm going to use emit, and I'm going to pass -1 here. So the saved jail actors thing is a stream where the effect type is IO and the value type is int. Now on this lambda, we can return a stream of a different type. Now, if the type is different, then the final return type is going to be the lowest common ancestor of the original type and this new type. And I chose the int type because it's the same here, so I'm going to type in int as the type declaration. If you choose to emit, for example, a string here, the return type will be something different, maybe any val or any or something like that, and this decreases the type safety of your streams. So make sure return a stream which contains values of the same type as before so that you don't mess up your types. Of course, you can use the error inside, so if you want a more complex way of emitting -1, you can use eval, and I'm going to say IO with, and I'm going to print something, so print line error occurred, and I'm going to inject my error. Then I'm going to return -1 in this IO. So let me go ahead and use this one instead. So error handled actors compile drain, and I'm going to not have any stack traces here. So Henry Cavill, error occurred, persistence layer failed, but this did not crash the stream, but rather terminated it without continuing to fetch more values. Another way of handling errors is to use the attempt method, which will turn your stream of plain values into a stream containing an either. So I'm going to have, let's call this attempted saved jail actors or something like that. This is going to be a stream where the effect type is IO, and instead of int, you're going to have an either where the undesirable type is throwable and the desirable value is int. And the way that you do that is to say saved jail actors.attempt. Then you can handle these eithers using the regular transformations like flatmap or evalmap in this case. So let's say attempted processed, for lack of a better name, and I'm going to use attempted jail actors dot eval map, and in case I get a left with an error, I'm going to return, let's say, IO with error, and going to inject the error inside, and I'm going to use debug, and in case I get a right with a value, I'm going to use IO, let's say successfully processed actor ID, and I'm going to use the value here, and then I'm going to pass another debug. Now let's see what happens in the console if I try to use this one in main. So notice that we have Henry Cavill, and we've apparently failed right here at this stage. Let's try more actors, because we are using a random generator. So Henry Cavill was successfully saved, so successfully processed actor ID 0. Gal Gadot was also saved, so successfully processed actor 1. And Ezra Miller sadly failed, and here our stream terminated with this particular error. All right, so this is how attempt runs. All right, so in this video we looked at pipe and two ways of doing error handling inside streams. The next thing that I want to show you is resource, or resource management. And in the Cats Effect course, I describe resource utilization in terms of effects in great detail, but here in streams, I'm going to show you how you can manage a resource inside the stream such that every single value or every single effect processed by that stream can use that resource independently. So let's assume that I'm going to create a case class database connection, for instance, with a connection string or a URL or something. So URL as a string, and I have some methods to acquire and release some connections to the database. So let's say acquire connection that takes a URL as a string, and this returns an IO of database connection. So database connection. And to keep things simple, I'm going to say IO, and then here I'm going to say print line getting DB connection, and I'm going to return a database connection with this particular URL as an argument, of course. And I'm going to create another method called release that takes a connection as database connection, and I'm going to return an IO unit. And I'm going to say IO print line, say releasing connection to, and I'm going to use connection.url for debug purposes. Okay. So we have some methods here that return an IO either containing a database connection or an IO unit to release that particular connection. Now, this database connection will act as a resource. So if, for instance, we want to process the stream of actors and we want to use the same database connection for the entire stream, we can do that with the bracket pattern. The bracket pattern is very similar to how regular effects like IO works. So I'm going to say, let's call this managed jail actors as a stream of IO and int, and I'm going to use stream.bracket, And stream.bracket takes two arguments, an acquire function that returns an effect. So I'm going to have acquire, and I'm going to say acquire connection with a particular URL, like, I don't know, jdbc://mydatabase.com or something like that. And the release callback, so I'm going to use a release here as the reference to the method, but you can also use a function value here. So this release method was turned into a function value. So this will be a stream of I/O and database connections. So notice that we obtained a single database connection. Of course, we can say flat map on that. And considering the connection that this stream contains, then I can process a stream using this resource. So I can say, for instance, saved jail actors, or some other method that uses this particular connection to save every single one of the jail actors into the database. For example, I can say eval tap, and I can pass a function from an actor ID to an effect that returns whatever else, because I'm going to maintain the actor ID as the value type of my stream. So I can say IO saving actor, let's say actor ID 2, and I'm going to use the connection, so connection.url, and then I can say debug. So this expression returns a stream where for every actor I'm going to perform this particular effect that probably relies on this connection. So this is where you would actually store the values in your database, but I will also keep the values of the original stream. Okay, and this manage jail actors is still a stream of IO and int. So if I try to push that to main, we're going to see all these effects being printed to the console. But of course, this persistence layer can fail because I've added some random number generators, and so without some error handling, this stream will fail. But you already have the tools that we described. All right. So this is how you can manage a resource inside a stream, so that you can process every single element in your stream using that particular resource. Now, another thing that I want to show you here is merge and concurrent stream execution. So we can use a merge to interleave several streams that are running at the same time. So this is diving into the concurrency land. So let's say I'm going to push all of these Justice League actors in one stream, let's say 2 actors per second, and I'm going to push the Avengers actors, let's say 1 per second or 3 per second or something like that. So I'm going to have, let's call this concurrent jail actors as jail actors dot eval map, and for every actor I'm going to return an IO that sleeps for a bit and just pushes that same actor. So I'm going to have thread sleep for, let's say, 400 milliseconds and then push that same actor, and I'm going to do the same for the other actor stream. So I'm going to have concurrent Avengers actors as Avengers actors dot eval map, and assuming an actor, I'm going to return another IO with a very similar thing. So I'm going to do a thread sleep for, let's say, 200 milliseconds and then push that actor. Now we can merge these two event streams, assuming that they come from different places in your backend application. You can interleave these actors and then push them somewhere else. So I can say merged actors as concurrent jail actors dot merge with concurrent Avengers actors. And this resulting stream is a stream of the effect type IO and actor, of course. And these two concurrent streams will basically interleave regardless of how they're actually being built. So the FS2 runtime will take care to merge these two streams all together. So if I say merged actors, and I'm going to push this to main, and I'm going to add a debug at the end. So debug and another debug so that we can print every single actor that's being merged. Let's see how this application works. So look at that. We have Scarlett Johansson, we have some Avengers actors, we have some Justice League actors, and notice how these values are interspersed in the console. Now, of course, the relative order of elements inside each and every stream is maintained. So notice that the Avengers actors start from the number 6, so 6, 7, 8, 9, 10, 11, and 13, because I think I've missed the number 12 in my count. So we have 11 and 13. I forgot that. And we have 0, 1, 2, 3, and so on and so forth for the other stream. Right? So the relative order of elements inside each stream is maintained, but the merge between these two streams is non-deterministic and concurrent. There's also another transformation that's called concurrently, that will simply run two streams at the same time, and this is particularly useful if you want two streams to produce different effects, but you want to run them concurrently because you have some internal logic in your backend application that deals, for instance, with the same resource. So this example, as producer-consumer, will probably illustrate what I mean. So I'm going to create a queue, which is the buffer for the producer-consumer problem, and this is an IO of type Q that I'm going to import from cat's effect std. So Q, where you have the effect type IO and the value type actor, and I'm going to have my Q dot bounded, and I'm going to have the number 10 here. So we have a buffer at most 10 elements big, and I'm going to have my concurrent system as the following. I'm going to have stream.eval with this queue, so I'm going to force the evaluation of this queue inside a stream, and then I'm going to call flatMap on that. So considering I have my queue inside the stream, I'm going to create a producer stream and a consumer stream. So I'm going to have my val producer as a stream of type IO and unit, and another one of the same type. So I'm going to call this consumer, and then I'm going to run them at the same time. So I'm going to have producer.concurrently with consumer. And this is a composite stream. Now, this is particularly useful for streams whose value types are unit. And I'm going to define my producer and consumer streams. Let's say I'm going to have my GL actors, and I'm going to use eval tap. So eval tap will take a function from a value to an effect, but keeping the original values inside the return stream. So I'm going to have my actor, and I'm going to have IO with that actor.debug, so that as I can see which actor is being produced, and then I'm going to offer, that is push every single value here in this queue. So I'm going to use eval map in this case. So I'm going to have for every actor, I'm going to have q.offer on that actor. So q.offer basically means in queue. And then I'm going to throttle this stream. So I'm going to use metered. Metered means that at most one value or effect is going to be produced per the duration that I'm going to pass inside. So 1.second. So this is a throttle at 1 effect per second. Now, of course, I need to import the second extension method. So I'm going to import Scala, concurrent, duration, everything. So I have my second extension method. So the producer will produce at most 1 actor per second in my GL actors stream. Now the consumer will have stream dot, and because the consumption of items from an effectfful queue is quite common, stream has a constructor to say from queue unterminated or non-terminated, and there are a bunch of overloads. So I'm going to use from queue unterminated, and I'm going to pass my little queue. And for every actor inside, I'm going to use eval map. And for every actor, I'm going to use IO with a string consumed actor. And then I'm going to say debug so that I can print that to the console. And to turn this into an IO unit, I'm going to use void. All right, so we have a producer stream and a consumer stream, and I'm running these two at the same time. So let's do this concurrent system in main, compile, drain, and let's see it running. All right, so notice that the producer is very slow, and as soon as an item is being produced, the consumer fetches that and consumes it and prints it to the console. And of course, when the collection is done, then the entire stream terminates. So these are some of the more advanced features of FS2. Now, this library is very complex, very powerful, and very rich. So there's much more to learn that we were able to discover in this simple mini-series. If you like this video, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. Check me out on Twitter and LinkedIn for fresh updates on upcoming material, and check out the Rock the JVM website for hundreds of hours, literally, on the Scala, functional programming, CATS effect, and so much more. Until next time, I'm Daniel, signing off.